Hello, and welcome to the quiet cosmos. Tonight, the destination is a pair of neighbours, the two worlds that circle nearer to the Sun than the Earth ever does. And a single, quiet question sits underneath everything that follows. What does air actually decide about a planet's fate? Venus and Mercury started from almost the same rough beginning. Two balls of rock born in the same hot, crowded region of the young solar system. And yet one wrapped itself in an atmosphere so heavy it would crush an ordinary machine within minutes, while the other kept almost nothing at all. A bare stone sitting nearly naked under full sunlight. One is close to a twin of Earth in size. The other is small enough to fit inside Earth many times over. Before that journey properly begins, a small note. If slow, careful science like this is the kind of company you like at the end of a long day, a quiet like or a subscribe helps this small channel find more of the people already searching for exactly this kind of story. It costs nothing more than a moment, and it is the only thing this channel will ever ask of you tonight. Tonight's slow, unhurried journey drifts first into the thick, scorched air smothering Venus, then out onto the silent, cratered plains where Mercury has almost no air left to keep. So, settle in, let the evening grow heavy, and let two small worlds close to the Sun tell their own quiet story about what a planet keeps and what it loses in the air wrapped around it. Of the four rocky worlds circling near the Sun, two sit closer to it than Earth ever does, Venus and Mercury, and tonight's whole route stays with only these two. Mercury sits nearest of all, a small scorched stone that would look lost standing beside Earth. Venus sits just beyond it, close enough to the Sun that it never strays far from the morning or evening sky, and close enough to Earth in size that early observers once mistook it for a twin. Between them, these two worlds cover nearly the whole range of what a rocky planet can become once given or denied an atmosphere. One buried under a suffocating blanket of its own air, the other left standing almost bare against open space. A rocky planet does not choose its own air the way a person chooses a coat. Their starting positions do not explain that difference by themselves, and their starting size does not explain it either. The explanation, patient and slow, is what tonight's route is really about, unfolding quietly, one small piece at a time, from the first shared beginning to the very last comparison. Venus comes close enough to Earth in size that people once called it Earth's twin, at least on paper. Its diameter runs to roughly 95% of Earth's own, and its mass comes out to somewhere around 81.5%. Numbers close enough that early textbooks sometimes listed the two planets side by side as a matched pair. Stand the two planets side by side, and the difference would barely register to the eye. One slightly smaller sibling standing next to the other. Even their bulk density, the average weight packed into each cubic meter of rock, lands close enough that early planners once imagined gentle clouds rather than a furnace waiting underneath them. That resemblance stops the moment the comparison moves from size to surface, because nothing in those numbers predicts the world actually waiting beneath Venus's clouds. A planet can match Earth almost perfectly on paper and still turn out completely unlivable in practice. Two planets born nearly the same size can still end up as different as fire and stone, and Venus and Earth remain the clearest proof of that anywhere nearby. Mercury holds the opposite record among the rocky planets, the smallest one of them all, at roughly 4,879 kilometers across. That is smaller than two moons found elsewhere in this solar system, Ganymede and Titan, both larger across than the small planet they merely orbit near. Mercury is not a giant cousin scaled down to fit a tighter orbit. It is genuinely tiny, closer in bulk to a large moon than to a proper planet, small enough that early telescopic observers sometimes struggled to resolve any real detail on its disk at all. Its gravity and its history both carry the marks of that small size, from the shape of its core to the thinness of whatever air still clings to it. Everything about how thin its air has become traces back, at least in part, to simply not having much mass to hold anything down with. In the end, a small planet keeps only what it can actually afford to hold. And Mercury's whole story grows directly out of that simple limitation. Venus circles the Sun at an average distance of around 108 million kilometers, close enough that a single trip around takes only about 225 Earth days. From that distance, the Sun would appear noticeably larger and brighter in Venus's sky than it does from Earth, without ever coming close to the furnace-like glare felt on worlds nearer still. Even that mild boost in sunlight plays only a small role in the story of Venus's heat, compared with what its own atmosphere does on its own. Venus completes its short year at a steady, unhurried pace, tracing a nearly circular path with very little of the stretching and squeezing that mark more eccentric orbits elsewhere in the solar system. That circular path keeps conditions remarkably consistent across the whole of a Venusian year, with none of the seasonal swing a more elongated orbit would bring. Short year, close orbit, size close to Earth's own. These were the ingredients Venus started with, long before its atmosphere quietly decided everything else about the world it would become. Mercury circles much closer still, at an average distance of only around 58 million kilometers from the Sun. Both of these inner worlds spend their entire orbit inside the path Earth traces around the same star, never once straying beyond it. Mercury's short, tight loop keeps it constantly bathed in far more sunlight per square meter than Venus receives, let alone Earth, sunlight strong enough to make its daylight side one of the harshest places anywhere nearby. That proximity should, in principle, make Mercury the hottest world nearby, simply by virtue of sitting closest to the source of all that heat. It does not. And the reason why becomes one of tonight's central threads once the two atmospheres, or the near lack of one, are properly compared side by side. Later spacecraft have measured that surface heat directly, confirming numbers early theorists could only estimate from a distance using sunlight and geometry alone. Closeness to the Sun decides only part of what a planet becomes. Neither Venus nor Mercury has a single moon anywhere in orbit around it. Of all the planets in the solar system, these two alone circle the Sun completely alone, with no smaller companion trailing along beside them the way Earth's own moon does. Every other planet, from tiny Mars to giant Jupiter, keeps at least one moon in tow, some of them keeping dozens. Even Mars, barely half the size of Earth, still carries two small moons of its own. Venus and Mercury share that particular emptiness, a small, quiet detail easy to miss next to the louder differences in their atmospheres. But one more thing the two of them hold in common before their stories properly diverge tonight. Astronomers have searched carefully for any small, undiscovered moon around either planet and found nothing convincing after decades of looking. No tides raised by a passing moon have ever pulled at either surface. Without a moon, a planet simply keeps whatever rhythm its own spin and orbit give it, nothing borrowed from a companion overhead. Both worlds formed inside the same hot, rocky inner region of the young disk of gas and dust that eventually became the solar system, closer to the infant sun than the icy zone further out where the giant planets took shape. That inner region ran too hot for ice to survive as solid material, leaving mostly rock and metal for young Venus and young Mercury to build themselves from. Earth formed from broadly similar material a little further out again, holding on to some water locked inside its rocks as it assembled from the same swirling disk. Astronomers sometimes call that boundary the frost line, the rough distance beyond which ice could survive the heat of the young sun. Small as it looks on the scale of the whole solar system, that difference in starting distance still set three rocky worlds on three very different paths. Two of them destined to end up almost completely dry. Their gravity tells a different story than their birthplace does. A reminder that a planet's fate rarely traces back to just one single cause. Venus pulls at nearly the same strength as Earth, its surface gravity coming out to roughly 90% of what a person would feel standing on Earth's own ground. Mercury pulls at a little over a third of that, its small size leaving it with comparatively little mass to hold anything close to its surface. A person who weighs a certain amount on Earth would weigh noticeably less standing on Mercury, and only slightly less standing on Venus. Spacecraft engineers factor that same gravity difference directly into fuel calculations, since escaping Mercury's pull takes noticeably less effort than escaping Venus's. That single difference in pulling power, more than almost anything else tonight, quietly decides how easily each world can keep hold of a passing molecule of gas, long enough to build a real atmosphere around itself. Gravity behaves like a slow, patient net stretched around each planet. And not every net is woven the same. Rarely the flashiest number in a planet's profile, gravity quietly shapes almost everything else that follows. Seen from Earth, these two worlds could hardly look more different. Venus is the brightest planet in the entire night sky, a steady, brilliant point often mistaken by new observers for a low aircraft light or an approaching star. Mercury, by contrast, stays so close to the sun's own glare that most people never notice it at all, visible only briefly near sunrise or sunset on the clearest of evenings. Venus dominates the sky, unmistakable even to someone who has never looked through a telescope, and ancient sailors and travelers used it as a dependable point of reference long before formal astronomy existed. Mercury, by contrast, appears in only a handful of ancient records, each one describing a fleeting, easily missed glimpse near the horizon. It hides in plain sight, a few finger widths from the sun, and has done so for every human who has ever looked up, ancient or modern. Even a whole planet can spend its whole existence hiding in the glare of something far larger and brighter than itself. Their names arrived from Roman mythology in almost opposite moods. Venus carries the name of the goddess of love and beauty, a fitting match for the brightest, most eye-catching planet in the sky. Mercury carries the name of the swift messenger god, always hurrying, never straying far from the master he served. Ancient skywatchers gave that second world a name built entirely around speed and closeness to a more powerful source, long before anyone measured an actual orbit or understood why the real planet never wanders far from the sun. Other cultures gave the same 2 points of light their own names and their own stories. long before anyone connected them to the physical worlds now studied by spacecraft. Several other ancient cultures, working entirely independently, arrived at broadly similar associations, linking the brightest point in the sky to beauty and the fastest moving one to speed or messages. Two myths, one about love and one about a hurried messenger, settled quietly onto two small, very different worlds. Both worlds were born rocky. Both carried enough volcanic activity early on to vent gas up from their interiors. And both, in principle, had a genuine chance at wrapping themselves in some kind of air. Their basic ingredients ruled neither one out from the very start. Volcanic gas alone never guarantees a lasting atmosphere. It only opens the very first door toward one. And whatever a young planet vents still has to survive there long enough to matter. A young Venus and a young Mercury likely looked more alike in the earliest chapters of their history than they do today. Two scorched, freshly formed rocks venting steam and gas into the thin space around them. Whatever came afterward, it was not a difference in raw material, since both worlds were built from broadly the same mixture of rock, iron, and trapped gas. Something else, something slower and quieter, decided how their story continued over the billions of years that followed. That slower decision is the one tonight's route follows closely. Only one of these two worlds kept that early air. The other lost almost all of it. And the gap between those two outcomes is exactly what tonight's slow route is built to trace. From the heavy, crushing clouds wrapped around Venus to the bare, sun-scoured plains left behind on Mercury. Their starting size, their starting orbit, and their starting mix of rock and metal made that outcome obvious to no one in advance, not to any observer watching the two worlds cool in their earliest years. The air itself wrote the remainder of the story, layer by layer, over a stretch of time longer than almost anything else described on this channel. No single moment marked that turning point clearly. It unfolded gradually, across a span of time too long for any single event to explain on its own. Tonight follows that story from one heavy, hidden surface toward one lying almost completely open to the sky, without ever needing to guess at what came before either beginning. The air wrapped around Venus is almost entirely carbon dioxide, making up somewhere near 96.5% of the whole atmosphere. Nitrogen accounts for most of what remains, a little under 4%, with only faint traces of other gases scattered through what remains, sulfur dioxide among them. Earth's air, by comparison, is mostly nitrogen, with just a modest slice of carbon dioxide mixed in. Ordinary Earth air itself carries roughly 4 parts nitrogen for every 1 part oxygen, with carbon dioxide barely registering at all. On Venus, almost nothing plays that role of a light background gas. Carbon dioxide simply dominates from top to bottom of the whole atmosphere. Even the faint traces matter more than their tiny share suggests, since gases like sulfur dioxide feed directly into the clouds that hide the surface from view. Nearly matched in size, Earth and Venus carry almost completely different mixtures of gas, one light and breathable, one dense and hostile. Stand on the surface of Venus, if a person somehow could, and the air pressure alone would be roughly 92 times what it is at sea level on Earth. That is close to the crushing weight felt at around 900 meters down in Earth's own ocean, deep enough that ordinary submarines need reinforced hulls simply to survive the trip. Venus has no need of a submarine, because the whole planet already sits under that same weight of air at every point on its surface. That kind of pressure would crush an ordinary submarine hull built only for shallow diving, and it does so almost instantly rather than gradually. Engineers designing anything meant to survive on Venus's surface start from that single number before considering heat at all, since pressure alone can crack a poorly built hull long before the temperature finishes the job. Smothered by an ocean or smothered by an atmosphere, the crushing weight feels much the same, and Venus proves it without a drop of water anywhere in sight. Venus's surface holds an average temperature of around 465 degrees Celsius, hot enough to melt lead and zinc outright rather than merely soften them. Spacecraft landing gear, camera lenses, and electronics all face that same heat the instant they touch down. No liquid of any familiar kind could survive exposed on that surface for more than a moment. Instruments sent to measure that heat directly have had to be built almost from scratch each time, since ordinary electronics designed for Earth conditions fail almost immediately inside it. For comparison, an ordinary kitchen oven rarely climbs much past 250 degrees Celsius, less than half of what the Venusian surface holds as its daily average. Metals that seem permanent and solid on Earth simply run liquid there, pooling instead of standing as any kind of familiar landscape feature. Nothing soft survives that heat for long. Day and night, across a whole planet, sits a temperature usually reserved for industrial furnaces. Venus holds the title of hottest planet in the solar system, hotter even than Mercury, despite orbiting almost twice as far from the Sun. Mercury sits closer to the furnace and still loses the contest for raw heat. Distance from the Sun, it seems, is not the deciding factor at all. Early astronomers working only from telescopes actually assumed Mercury would prove the hotter of the two, simply for sitting nearer the Sun, and direct measurement eventually overturned that reasonable but mistaken guess. Mercury's daylight side does climb to blistering extremes of its own, closer to the Sun and fully exposed to its light. Even so, none of that raw exposure manages to beat the heat trapped and recycled endlessly within Venus's own thick blanket of gas. A planet's own atmosphere can apparently outdo the Sun itself at the job of heating a surface. Something about Venus itself, not its position in space, is doing nearly all of the heating. A lesson that reshaped how scientists think about heat on any rocky world. Not just this one. That extreme heat comes from a runaway greenhouse effect, a process where a thick blanket of carbon dioxide traps incoming sunlight as heat far more effectively than it lets that same heat escape back out into space. Sunlight passes through the upper atmosphere easily enough and warms the surface below. The energy trying to leave again, now traveling as infrared heat rather than visible light, finds itself absorbed and re-radiated over and over by that same thick blanket of gas, unable to slip back out into the cold of space with any real speed. Earth has a mild version of the same effect, gentle enough to keep the planet comfortable rather than scorched. A single degree of extra trapped heat compounds slowly into hundreds once the process runs unchecked for long enough. Venus never found a way to stop the process once it got started, and the heat built up layer upon layer until it settled at a scorching, stable extreme. Because that atmosphere is so massive and so constantly stirred, the night side of Venus stays almost exactly as hot as the day side. On Earth, night brings real relief, the ground cooling steadily once direct sunlight disappears. On Venus, the thick air carries heat around the whole planet faster than any single patch of ground can cool. A traveler circling Venus at any altitude close to the ground would find no meaningfully cooler hemisphere to land on, no equivalent of a shaded, breathable evening anywhere on the map. Earth's own night side cools by tens of degrees within a matter of hours. Venus barely shifts by a handful. Instruments placed on any future lander would need to be built to the same extreme specification, regardless of which side of the planet they happened to touch down on. There is no cooler hemisphere to retreat toward, no shaded valley offering any real relief. Day or night, the surface sits under the same relentless heat. The clouds wrapped around Venus are made mostly of droplets of sulphuric acid rather than water, an entirely different kind of weather from anything familiar on Earth. Those clouds never once part enough to let ordinary sunlight through as a visible disk reaching the ground below. Anyone standing on the surface, somehow shielded from the heat and pressure, would see only a dim, diffuse glow rather than any recognizable sun overhead. Unlike Earth's water clouds, these acid droplets never fall as any kind of rain reaching solid ground, evaporating again long before they could ever land. Whatever moisture briefly forms in Venus's upper air stays trapped in an endless, unbroken cycle far above the surface. Sensors designed to detect rainfall on Earth would find nothing at all to measure anywhere within reach of the Venusian surface. A sky that never truly rains, sitting above ground that has likely been dry for a very long time. Permanently sealed shut, an acid sky hangs over the whole of Venus without one clear break anywhere in it. Those acid clouds sit at altitudes of roughly 45 to 70 kilometers above the surface, forming one continuous, unbroken shroud that wraps completely around the planet. No gaps interrupt that shroud, no clear patches drift open the way clouds thin and part on Earth. Seen from directly above, that shroud gives Venus its familiar pale, almost featureless look in ordinary photographs. Nothing like the blue, swirled marble of Earth or the banded face of Jupiter. Only instruments built to see past visible light can find any real structure inside it at all. Any future high-altitude balloon mission would need instruments built to work entirely by touch and radar, since sunlight never properly breaks through to guide a camera below. The shroud simply never lifts. From space, Venus appears as a smooth, featureless pale globe, precisely because that layer never breaks. Whatever lies underneath stays hidden behind it. Day after day, year after year, the same way it has for as long as the planet has carried an atmosphere at all. Curiously, one narrow band inside that same atmosphere, somewhere around 50 to 65 kilometers up, carries temperature and pressure remarkably close to conditions at Earth's own surface. A person floating at exactly that altitude, protected only from the acid itself, would feel roughly familiar warmth and roughly familiar air pressure pressing in. Engineers studying possible future balloon missions to Venus have specifically pointed to that same narrow band as one of the few genuinely survivable places anywhere on the planet for delicate equipment to operate for extended periods. It remains, even so, a layer suspended inside acid clouds rather than any true habitable ground, And even within that milder pocket, the surrounding droplets would still make an unprotected visit entirely out of the question. It is a strange, narrow pocket of mildness, suspended high above an unlivable surface far below. Scientists studying whether anything could ever survive on Venus tend to look first at that one gentle layer, not at the crushing furnace underneath it. Taken as a whole, the mass of Venus's atmosphere is enormous, outweighing the mass of Earth's entire atmosphere by roughly 93 times over. Earth's air, spread across a planet nearly the same size, is almost feather-light by comparison. 93 Earth atmospheres stacked together would already be an almost unimaginable weight of gas on their own. Venus carries that entire weight around a single planet barely larger than Earth itself. The planet's modest size gives no hint, at first glance, of an atmosphere quite this heavy. Engineers modeling future missions treat that single figure as one of the first numbers checked before any other design decision is made. Since a parachute built for Earth's air would behave completely differently the moment it entered anything this dense. Venus carries close to 100 Earth atmospheres worth of gas stacked over every square meter of its surface. That one number explains the crushing pressure below better than almost any other measurement taken of the planet. In March 1982, the Soviet lander Venera 13 touched down on the surface of Venus and kept working for about 127 minutes before the heat and pressure finally overwhelmed it. In that short window, it sent back the first color photographs ever taken from the surface of another planet. Every device on board had been built specifically to survive, however briefly, conditions that would crush and melt an ordinary spacecraft within minutes. News of that brief, successful landing reached scientists back on Earth as one of the clearest proofs yet that engineering could, however briefly, outlast conditions long assumed impossible to survive at all. Every minute beyond the first hour counted as bonus data nobody had fully expected to receive. Ground controllers monitoring the signal in real time reportedly had little idea how much longer the lander could last and treated every extra minute as a small, welcome surprise. 2 hours of working time on a world where 2 hours already counts as remarkable endurance. Earlier missions paved the way for that brief success. Venera 7 reached the surface and sent back data in 1970, the first spacecraft from any country to transmit from the surface of another planet. Venera 9 followed in 1975, sending back the very first images, black and white and grainy, of the ground beneath those endless clouds. Both missions were part of the wider Soviet Venera program, a sustained, decade-spanning effort to understand a planet that kept destroying almost every machine sent toward it. Each small success built directly on the failures and partial successes that came immediately before it. Progress there came in minutes, not leaps. Both landers relied on instruments built with knowledge gathered from even earlier failed attempts, learning exactly how quickly Venus could destroy an unprepared machine. And each generation of hardware ran a little longer than the one before it. Each mission taught engineers a little more about exactly what kind of conditions were waiting below. Every one of those landers was built as a small, dedicated pressure vessel, designed from the very start to survive, at least for a while, pressure and heat that would finish off an unprotected machine in minutes. Thick metal shells, specially cooled electronics, and reinforced camera housings all worked together to buy each mission a handful of extra minutes on the surface. Some carried simple cooling systems built around blocks of ice or chilled fluid, designed to buy just enough extra time before the surrounding heat finally won out. None of that engineering could hold back Venus's conditions indefinitely, only delay the inevitable by a useful margin. Designers tested materials and seals in chambers built on Earth to simulate, as closely as possible, the pressure and heat waiting on the real surface. Though nothing built on Earth could fully replicate those conditions before an actual landing proved it one way or another. Each lander was, in effect, a small, doomed submarine built for a sea of scorching gas, not water. An important clue about Venus's past hides in its clouds. The ratio of heavy hydrogen to ordinary hydrogen there runs roughly 150 times higher than the same ratio measured on Earth. That kind of skew does not happen randomly. Scientists measure that particular ratio using instruments sensitive enough to tell heavy hydrogen apart from its far more common, lighter form, even in vanishingly small quantities. A skew this large does not appear by chance in any planet's atmosphere. Something specific in Venus's history had to produce it. That same ratio has since been checked and rechecked by multiple independent missions, each arriving at numbers close enough to confirm the original measurement was no rare instrument error. It points toward a planet that once held far more ordinary hydrogen than it does now. Hydrogen that has since mostly slipped away into space. Buried in the chemistry of the clouds, one small ratio opened a whole line of questions about water that might once have existed on Venus. That imbalance is best explained by the idea that Venus once carried far more hydrogen than it does today, quite possibly locked inside a large reservoir of water. Some models suggest that an early ocean, or something resembling one, could have sat on the Venusian surface long before any runaway greenhouse effect took full hold. Under that picture, rising temperatures would have broken the water apart into hydrogen and oxygen, with the far lighter hydrogen drifting off into space more easily than the oxygen left behind. Researchers reach for this kind of hedged language deliberately, since no lander has ever recovered direct physical evidence of standing water from Venus's ancient surface. Every version of the story stays anchored to indirect chemical clues rather than anything seen or touched directly. That hydrogen clue is the strongest thing anyone has, and it still falls short of proof. Somewhere behind that one measured ratio sits the quiet, unproven memory of a whole vanished ocean. Some models go further still and suggest that early Venus could have held an ocean comparable in scale to Earth's own, spread across some portion of a surface that looks nothing like an ocean world today. Other estimates land far more modestly, closer to a few hundred meters of water spread globally rather than a full planetary sea. Neither figure comes from any direct measurement of ancient shorelines or seabeds, since nothing of that kind has ever been found preserved on Venus's resurfaced ground. Both numbers are built instead from careful modeling of how quickly water could plausibly have escaped over billions of years. Future missions, carrying more sensitive instruments, may eventually narrow that wide range considerably, though nothing currently on its way to Venus is built specifically to settle it. The honest answer likely sits somewhere inside that wide range, not at either extreme. Whatever its true size, that early water did not last. Something slow and irreversible turned an ocean or something close to one, into the driest, most hostile surface known anywhere nearby. The oxygen freed from that lost water most likely combined with minerals in the surface rock or escaped separately into space, while the far lighter hydrogen slipped away far more easily still. Heavier atoms simply have a harder time reaching the speed needed to escape a planet's gravity than lighter ones do. Over enormous stretches of time, that basic physics can strip a planet of its lightest elements almost completely, while leaving heavier ones mostly behind. Spacecraft measuring today's escaping gas can track this same process still happening at a much slower pace. Hydrogen continuing to leak away even now in far smaller amounts than whatever left in Venus's deep past. Comparing today's slow, ongoing leak against the far larger loss implied by the ancient hydrogen ratio helps researchers estimate roughly how long the original escape might have taken. The direction of the leak has not changed, only its speed. Whatever water once existed there left mostly through the narrowest possible door, one light atom at a time. Instruments studying Venus have also picked up a faint glow on its night side, a soft chemical light rather than any reflected sunlight bouncing back from elsewhere. That glow forms high in the same restless atmosphere already carrying the planet's clouds, produced when certain molecules recombine after being broken apart by sunlight during the day. Researchers first identified the glow using sensitive cameras built to detect faint light far below what any unaided eye could register. Similar chemical glows have since been spotted in Earth's own high atmosphere, though never studied anywhere near as intensely as the one wrapped around Venus. No lander has ever been positioned to study that glow directly from the surface looking upward, leaving orbiting spacecraft as the only vantage point available so far. It is far too faint for any human eye to notice without sensitive equipment. Nothing about it warms the surface or changes the overall picture of Venus's heat. Quietly, on the dark side of an otherwise blinding planet, a small chemical whisper keeps glowing. Ultraviolet instruments have tracked shifting levels of sulfur dioxide in Venus's upper clouds since the 1970s, rising and falling in ways that do not fully match a simple, steady pattern. One possible explanation is that fresh volcanic gas from below is periodically topping up the supply, feeding new sulfur dioxide into the atmosphere from underground. Another possibility points to ordinary atmospheric circulation, stirring older gas up from lower, more concentrated layers without any fresh volcanic source at all. Ground-based telescopes and orbiting spacecraft together have built a record stretching across 5 decades now, long enough to catch several rises and falls, but still too short to fully separate every possible cause. The record keeps growing every year. Whichever explanation eventually wins out, the sulfur dioxide record itself remains one of the longest continuously tracked measurements taken of any part of Venus. Researchers have not settled which explanation, or what mix of both, actually accounts for the pattern. The changing numbers themselves are real and well recorded, whatever their true cause involves. Venus has no strong magnetic field of its own, nothing generated deep inside by the kind of churning motion that powers Earth's field. On a bare, thin-aired world, that absence might strip away an atmosphere fairly quickly, exposed directly to the raw particles streaming outward from the Sun. Venus's atmosphere is so thick and so massive, though, that this missing field barely seems to matter for what the planet keeps day to day. Spacecraft measuring the space directly around Venus have found no trace of the deep, self-made field that wraps around Earth. What protection Venus does have comes from its own air, not from its core. Mass and pressure, in this case, do work that magnetism might otherwise have been needed for. Without its own magnetic shield, a planet can still manage to hold on to close to 100 times Earth's own weight of air. High above the surface, the winds inside Venus's clouds move far faster than anything ever stirs on the ground below, typically somewhere around 300 to 400 kilometers an hour near the cloud tops. Winds at that speed would flatten almost any structure ever built on Earth. By comparison, winds that fast are almost unheard of on Earth, where even the strongest hurricanes touch that pace only in brief, record-setting gusts. Venus keeps winds close to that extreme, blowing constantly, not as a rare storm, but as an ordinary everyday condition in its upper clouds. Up in those clouds, they simply blow, day after day, with no ground-level turbulence to slow them down. Measuring wind speed this high above an unreachable surface relies entirely on tracking how quickly cloud features drift, rather than any instrument placed directly in the wind itself. Nothing on the planet's surface hints at winds anywhere near that violent. The real weather on Venus happens almost completely far above anyone who might ever stand there. Those cloud-top winds carry the whole visible cloud layer around the planet roughly once every 4 Earth days, a phenomenon astronomers call superrotation. The clouds move far faster than the solid body underneath them, racing ahead in a tight, continuous loop above it. Astronomers first confirmed the pattern by tracking individual cloud features across successive images taken days apart, watching identical bright and dark markings sweep steadily around the whole planet. That same tracking method remains one of the main tools still used to study the phenomenon today. A full circuit that fast means a single cloud feature can complete several trips around Venus within the time it takes Earth's own weather systems to barely shift position. Something meteorologists studying Earth's atmosphere have nothing remotely comparable to measure it against. No other planet spins its air this far ahead of itself. Over and over, every 4 days without fail, a whole planetary cloud deck keeps outrunning the world it belongs to. At the equator, cloud-top wind speeds have been recorded running even higher than the usual range described a moment ago, with gusts clocked above 500 kilometers an hour in some measurements. Those numbers represent brief peaks rather than the steady, typical pace of the wind across the whole cloud deck. Instruments capable of resolving wind speed this precisely have only become available in recent decades, meaning earlier missions likely missed some of the fastest gusts entirely. Each new spacecraft arriving at Venus tends to push the recorded extremes a little further than the mission before it. A short gust at that speed carries enormous force, moving faster than almost any storm ever recorded on Earth's own surface, fast enough to strip loose material from almost any exposed structure in seconds. Scientists studying Venus's atmosphere treat these peak readings as a separate detail from the broader average wind speed described earlier. On Earth, only the very strongest recorded gusts have ever come close to that pace. What actually drives this superrotation? Clouds circling the planet many times faster than anything beneath them is still not fully explained. Some researchers have proposed that heating differences between the day and night sides of the planet pump energy into the flow in a steady, continuous rhythm. Others point instead to smaller atmospheric waves rippling upward from lower layers, nudging the whole system along gradually over time. Ground-based telescopes, orbiting spacecraft, and increasingly detailed computer models have all been brought to bear on the question over recent decades, each approach narrowing the possibilities without fully closing the case. and some of the strongest recent evidence comes from tracking how wind speeds shift subtly with both altitude and time of day. None of these explanations alone accounts for the full effect convincingly. It remains one of the genuinely open questions still attached to Venus's atmosphere. Studied for decades, a planet can still keep one of its own winds a mystery. Down at the surface itself, conditions could hardly be more different from the racing winds far above. The air there is so dense that it barely stirs any dust at all, moving sluggishly compared with the thin, fast-moving gas higher up. Walking through it would feel far closer to wading through water than to standing in any ordinary breeze. Early engineers designing Venus landers had to account for this heavy, slow-moving air just as carefully as they accounted for temperature, since even a light breeze at that density could exert real force against a spacecraft's hull. Nothing about the surface wind resembles anything a person standing there might casually call a breeze. And any dust that does eventually settle stays remarkably undisturbed for long stretches, since nothing at ground level carries enough force to lift it back into the air easily. The fastest weather on the whole planet and its calmest patch of air exist only a few dozen kilometers apart, one stacked directly above the other. Because Venus's clouds never part, ordinary cameras looking down from orbit see nothing but an unbroken, featureless haze. Almost everything known about the planet's actual surface has come from radar instead, which can send signals straight through those clouds and read the shape of the ground from how the echo bounces back. Early images of Venus, taken from orbiting cameras, showed nothing more than a smooth, glowing ball. No continents, no craters, no hint of any feature at all. Only once radar instruments were pointed at the same blank disk did an actual landscape finally begin to emerge from underneath it. Even modern optical telescopes on Earth, no matter how powerful, run into exactly the same barrier when they try to look directly at the Venusian surface. Radar simply ignores the barrier altogether. Radar effectively gave scientists a second kind of vision, built specifically for a world determined to hide its own face. Almost the whole of a planet's landscape mapped through echoes, not through light. NASA's Magellan spacecraft used that same radar technique to map roughly 98% of Venus's surface between 1990 and 1994. Before Magellan, most maps of Venus were little more than rough outlines, educated guesses filled in with sparse data. Magellan orbited Venus specifically built to send radar pulses downward and time how long each echo took to bounce back, translating that timing into a detailed picture of height and shape across the whole surface. Mission scientists spent years afterward turning that raw radar data into the maps still used by researchers today. Some regions were mapped multiple times from slightly different angles, letting scientists build a genuine three-dimensional picture of height and slope rather than a flat outline alone. Afterward, scientists had a detailed picture of mountains, plains, craters, and volcanoes stretching across nearly the whole globe. Few missions on their own have transformed understanding of any world as thoroughly as Magellan transformed Venus, turning a blank, cloud-covered sphere into one of the best mapped surfaces in the solar system within only a few years. Radar studies of Venus did not begin with Magellan. Ground-based telescopes and the pioneer Venus orbiter, working through the late 1970s, had already sketched a rough outline of major surface features years earlier. Those earlier passes relied on radio dishes pointed from Earth itself, bouncing signals across tens of millions of kilometers of empty space and waiting for a faint echo to return. Compared with an orbiter flying directly overhead, that distant approach could only ever resolve the very largest features, often blurring smaller ridges and craters into a single vague shape. Even with those limits, early radar astronomers managed to identify a handful of major features well before any spacecraft confirmed their existence up close, giving later mission planners a rough map to aim for. Magellan's later, sharper pass filled in nearly everything those earlier efforts could only hint at. Decades of patient, incremental radar work, stacked one mission on top of the last, slowly turned a guess into an actual map. That finished radar map showed a surface where volcanic plains cover somewhere between 80 and 85% of the whole planet. Lava once spread across nearly the whole surface of Venus, flooding older terrain and burying whatever came before it under fresh rock. By comparison, active volcanic regions on Earth cover only a small fraction of the planet's total surface, scattered mostly along narrow chains and isolated hotspots. Venus, instead, wears its volcanic history across nearly its own entire visible face, with almost no bare, unweathered rock of any other kind surviving in large quantities anywhere on the planet. A single dominant story, told again and again across nearly every stretch of ground mapped so far. Few other rocky worlds nearby show anything close to that scale of volcanic coverage. Mars and the Moon carry volcanic regions too, but nothing stretching across such an overwhelming share of the total surface. Venus, beneath its endless clouds, is in large part simply cooled lava that once spread across the whole planet. More than 1,600 large volcanoes have been catalogued on Venus, alongside many thousands of smaller volcanic features scattered across the plains between them. That makes Venus the most volcano-covered rocky planet known anywhere nearby. Some of these structures rise as broad, gently sloped shields. Others sit as small domes, barely a few kilometers wide. Counting them all took years of careful work sifting through the Magellan radar data, and researchers continue to debate how many of those thousands of features are truly separate volcanoes, rather than small events belonging to a larger, connected system. Earth, despite its own active volcanism, has nowhere near that concentration of individually mapped volcanic structures across a comparable stretch of surface. Most of Venus's volcanoes appear to have gone quiet long ago, leaving behind only their shape as evidence of what once happened there. In the end, a planet the size of Venus had room for thousands of separate mouths where molten rock once reached the surface. The tallest peak on Venus, Maxwell Montes, rises to around 11 kilometers above the planet's average surface level. Taller than Mount Everest, stands above sea level on Earth. It sits within a highland region called Ishtar Terra, one of the few areas on Venus that rises well above the surrounding lava plains. Climbers on Earth spend weeks acclimatizing to reach Everest's summit, battling thin air the entire way up. Anyone attempting the same climb on Maxwell Montes would face the opposite problem completely: air far too thick and far too hot for any equipment yet built to survive. No lander has ever reached or sampled that summit. Its slopes were mapped in detail only by the same radar surveys that charted the remainder of the planet. Its shape suggests it formed in some other way than most of the smaller volcanoes nearby. One mountain, quietly outranking Earth's highest point, hides the whole time behind clouds no camera has ever managed to see through directly. Venus shows no sign of plate tectonics in the way Earth experiences it. No network of shifting plates grinding against one another across the surface. Its crust behaves instead like one continuous shell, cracked and folded in places, but never broken into separate moving pieces, the way Earth's crust is. Instead of separate plates sliding past one another, researchers studying Venus have proposed a slower process where the crust deforms and flows gradually rather than breaking into distinct moving pieces. Whatever the exact mechanism, Venus clearly recycles its surface by different rules than Earth does, and comparisons between the two crusts remain one of the more active areas of ongoing planetary research. Scientists describe this as a stagnant lid, a crust locked in place rather than constantly recycled the way Earth's ocean floor is. Exactly why Venus never developed proper plate tectonics, despite being so similar to Earth in size, remains an open and actively studied question. By size, Earth's near twin ended up wearing a completely different kind of skin. Large impact craters on Venus are unusually few in number and spread remarkably evenly across the whole surface, rather than clustered thickly in some places and thin in others. That kind of even scattering suggests the whole surface was reworked in one broad episode, roughly 300 to 700 million years ago, rather than built up gradually over billions of years, the way most rocky surfaces are. Some researchers have proposed that this resurfacing happened through a single, overwhelming pulse of volcanic activity. Others favor a series of large but separate episodes spread across a somewhat longer stretch of time. Either version still points to a surface far younger than the planet carrying it. Exactly how sudden or how gradual that resurfacing really was is still debated among planetary scientists. The rough age range itself is fairly well supported by the crater counts alone. Young and evenly resurfaced, this face sits on top of a planet old enough to have collected far more scars than it actually shows. A fresh look at old Magellan radar images, published in 2023, spotted a volcanic vent near Ma'at Mons that appeared to have changed shape between two separate observation passes. The researchers behind that analysis were careful in how they described it, framing the change as a hint rather than a confirmed eruption caught in the act. If the interpretation holds, it would suggest Venus may still be volcanically active today, not simply a planet whose volcanoes fell silent long ago. No one has yet observed an actual eruption directly. Follow-up observations aimed specifically at confirming or ruling out further changes near the same vent are still being planned by researchers who study the original images closely. A single before and after comparison, decades apart, was enough to reopen a question many assumed had already been settled. Old data, looked at closely enough and long enough after the fact, can still turn up a hint that a supposedly silent planet has not gone quiet after all. Japan's Akatsuki orbiter reached Venus in 2015, arriving 5 years later than planned after its first attempt to enter orbit in 2010 failed outright. Engineers spent those 5 years reworking the mission's plan, waiting for the spacecraft's path to bring it back near Venus for a second try. That second attempt succeeded, and Akatsuki went on to study the planet's atmosphere from orbit for close to a decade, tracking its clouds, its winds, and its strange, restless weather. Akatsuki's cameras, tuned to wavelengths that can see through parts of the cloud deck invisible to ordinary optical instruments, have captured detailed views of cloud patterns changing over days and weeks. Those images have added considerably to what scientists understand about the strange, fast winds turning above the surface. And mission planners consider Akatsuki's recovery one of the clearer examples of the spacecraft earning a useful second attempt. Few missions get a genuine second chance at the exact same target after failing the first time. Akatsuki's slow, patient recovery turned a missed arrival into one of the steadiest long studies Venus's clouds have ever had. Space agencies have 3 new missions to Venus in development for the next decade: NASA's Veritas and Da Vinci, and the European Space Agency's Envision. Each one is built to look more closely at either the surface or the atmosphere than any earlier mission managed, using instruments far more sensitive than anything flown to Venus before. Veritas and Envision will map the surface in far finer detail than Magellan's original radar survey could. Da Vinci will send a probe descending directly through the atmosphere, sampling the air layer by layer on its way down. Together, the 3 missions represent the busiest stretch of Venus exploration in more than 3 decades, arriving after a long gap, during which the planet received far less attention than Mars or the outer solar system. After decades of relative quiet, Venus is due to become one of the most closely watched worlds in the sky all over again. Venus reflects around 3/4 of the sunlight that reaches it, more than any other planet in the solar system manages. That reflectivity comes almost entirely from its thick, unbroken layer of clouds, bouncing sunlight back into space before it ever reaches the scorching surface below. This is exactly what makes Venus shine so brightly in Earth's sky, often bright enough to cast a faint shadow on a clear, dark night. Ancient observers who tracked that brightness across the sky, long before understanding what caused it, built calendars and stories around its steady, predictable comings and goings. None of that brightness comes from any light Venus produces on its own. Every bit of it is simply sunlight, borrowed briefly and thrown straight back out again by a planet wrapped too tightly in cloud to keep any of it. Too hostile to visit for more than a couple of hours, this planet still manages to outshine every star in Earth's sky. All of it. The endless clouds, the racing winds, the volcanic plains mapped only by radar, sits on top of one heavy, scorched blanket of air wrapped around the whole planet. A world close to Earth in size ended up carrying an air blanket weighing nearly 100 of our own stacked together, hot enough to melt metal, thick enough to hide its own ground from every ordinary camera ever sent there. That is one way for a rocky world to answer the question of what to do with its atmosphere. It is not the only way. Neither their size nor their birthplace predicted which of the 2 neighbours would end up which way, and neither planet had any way of knowing at the very start which fate awaited it. Both outcomes, taken together, mark out the full range of what a rocky world can do with its air, from the heaviest blanket nearby to almost none at all. Somewhere close by, another small rocky world answered the very same question in almost the opposite direction, keeping almost nothing at all. Something links these 2 worlds together, even though their skies could not look more different. Venus wears the heaviest air of any rocky world near the Sun, a blanket so thick it leans on the ground with the weight of 100 skies. Mercury barely wears one at all, holding on to little more than a whisper of gas around bare rock. Only a short list of factors decides which fate a planet gets: how strongly its own gravity pulls on the gas above it, how hot its surface runs, how exposed it sits to the stream of charged particles pouring from the sun, and whether anything keeps refilling what constantly leaks away into the emptiness surrounding both worlds. None of these factors works alone, and each one leans on the others the moment a planet actually finishes forming. Turn one up or down, and the balance shifts a little. Turn several the same direction at once, and a whole planet can tip toward keeping its air for billions of years, or losing nearly all of it within a comparatively short stretch of that same span. A tipping point written into a world's chemistry long before anyone existed to measure it. Two neighbors sitting close to the same star ended up on opposite sides of that balance. Gravity first, heat second, wind and replenishment close behind, and the reasons come apart one at a time from here. Gravity sets a threshold scientists call escape velocity, the speed a gas molecule needs to reach before it can leave a planet for good, rather than fall back down under that same planet's own pull. Mercury's escape velocity sits at only about 4.3 kilometers per second, a fairly gentle wall as these things go. Venus asks for roughly 10.3 kilometers per second, almost as demanding as Earth's own 11.2. A narrow gap between two very differently sized worlds. That difference of only a few kilometers per second decides an enormous amount about what stays close to a planet and what drifts away from it forever. A molecule moving just below the threshold circles back toward the surface eventually, caught by gravity like a ball thrown that never quite clears a wall. A molecule moving just above it disappears into space and never returns, gone for good the instant it clears that particular line. Mercury's low wall is easy to clear. Venus's high wall almost never is. Heat plays its part too, because temperature is just the average speed at which molecules jostle about, and hotter gas moves faster. Lighter molecules also have an advantage a heavier one does not. For the same temperature, a light molecule, like hydrogen, darts around far quicker than a heavy one, like carbon dioxide, sometimes by a wide margin. Physicists call this slow, ongoing leak thermal escape, or sometimes Jeans escape, after the mathematician who worked out the physics behind it in careful detail. It never needs a dramatic event to happen. A planet simply loses its fastest, lightest molecules first, one at a time, day after day, for as long as it exists. Earth's own atmosphere loses a small trickle of hydrogen this same way, even today, though far too slowly for anyone to ever notice across an ordinary human lifetime. This kind of escape happens constantly and quietly, without any single dramatic burst marking the moment a molecule finally leaves for good. Given enough time, that quiet drip can reshape the whole character of a world's sky. Venus's gravity sits close to Earth's own, strong enough to hold onto gas that a smaller world could never keep for long. Even at nearly 500 degrees Celsius, carbon dioxide molecules are comparatively heavy, and heavy molecules rarely reach the speed needed to break free on their own. Occasionally, one gets a lucky, fast collision and slips past the threshold. Most simply do not. Even the fastest moving molecules near the top of that thick blanket usually collide with a neighbor and lose speed again, long before they ever reach the height and velocity needed to escape completely. The heat baking Venus is real and constant, but the planet's own pull is strong enough to keep almost all of that heated gas circling close to home instead of drifting off into space. Instruments monitoring the uppermost layers of Venus's atmosphere have measured this slow loss directly, confirming just how modest the rate really is. Mass, in this particular contest, is winning against temperature. Mercury's gravity is the weakest of the three, a feeble grip next to the pull holding Venus's blanket firmly in place. Its sunlit side bakes almost as hot as Venus's average surface, and it does so without any air to spread that heat around. Put a weak grip and a fierce local heat together, and lighter gases find it far easier to slip away. Hydrogen, helium, and other light molecules barely have to try. Helium, in particular, slips away from Mercury especially fast, and whatever small amount remains gets replenished mostly by fresh helium arriving from the solar wind itself. Heavier atoms also get a meaningful boost toward the escape threshold under conditions like these. Researchers modeling this loss rate have found it broadly consistent with the very thin exosphere actually observed surrounding the planet today. The two planets share plenty, but this particular combination belongs to Mercury almost alone. Sitting closer to the Sun brings a second penalty beyond the heat itself. A far stronger dose of the solar wind, the constant stream of charged particles racing outward from the Sun's outer atmosphere. That wind thins out the farther it travels, the same way light from a lamp fades gradually with distance. Anything orbiting close in gets hit by a denser, faster stream than anything orbiting farther out. Spacecraft instruments have measured this thinning directly, tracking how the density and speed of the solar wind fall away the farther any given detector travels from the Sun. For the two innermost planets, that penalty is not a minor detail. It shapes how much gas each one can hope to keep on top of whatever heat and gravity already decide. This same basic thinning pattern shapes conditions for every planet in the solar system, not only the two innermost ones. Distance from the Sun taxes a planet twice over, once through warmth and once through wind. Mercury sits directly in the path of that stronger wind with almost no shield of its own standing in the way. Its thin haze of gas gets swept outward, stripped from the surface, and scattered into space within days rather than centuries. Fresh atoms knocked loose from the rock below drift up to replace what was lost, only to be blown away again soon after. The whole arrangement behaves less like a steady coat of air and more like a fountain that never stops running and never quite fills a basin. Researchers studying Mercury sometimes describe the whole exosphere less as a stable layer and more as a population of atoms, each one only passing through for a short visit. What surrounds Mercury today is not the same gas that surrounded it yesterday. Nothing there ever settles long enough to be called an atmosphere in the ordinary sense. Venus carries no magnetic field of its own making, nothing generated deep inside by a churning molten core the way Earth's field is. And yet it is not defenseless. As the solar wind strikes the upper layers of its thick atmosphere directly, the interaction bends and drapes the Sun's own magnetic field around the planet, weaving together something researchers call an induced magnetosphere. Spacecraft flying through this induced magnetosphere have measured its shape directly, finding it far smaller and far less symmetrical than the true magnetic bubble surrounding Earth. It offers only partial protection, nowhere near as complete as a true internal field would provide. Even so, that borrowed shield helps deflect a portion of the incoming particles that would otherwise strike the atmosphere at full force. Comet-like structures, known as ion tails, sometimes form downstream of this induced magnetosphere, stretching away from Venus in the direction the solar wind happens to be blowing. This planet, with no field of its own, has still found a way to fashion a rough kind of shelter out of the very wind trying to strip it bare. Venus also has something Mercury today largely lacks: an active supply line. Continuing volcanic activity deep within the planet keeps adding fresh carbon dioxide and other gases from the interior back into the atmosphere above. Whatever slips away into space through those slow, patient processes gets balanced, at least in part, by whatever the planet's own volcanoes keep releasing from below. That balance does not need to be perfect to matter. Estimating exactly how much gas Venus's volcanoes add back each year remains genuinely difficult, since so much of that activity happens beneath clouds no camera can ever see through. Even a partial refill, kept up over billions of years, can hold a thick atmosphere roughly steady rather than letting it drain away for good. Ground-based and orbital telescopes continue monitoring these gas levels closely, hoping eventually to catch a genuine eruption in progress rather than only its aftermath. Keeping an atmosphere fed is a very different game from having stopped feeding it long ago, and Venus and Mercury landed on opposite sides of that particular game. Mercury's own volcanic plains tell a very different story about timing than the plains found beneath the clouds of Venus. They formed billions of years ago, early in the solar system's history, and the volcanic activity behind them has since gone largely quiet. Spacecraft images of those old plains show none of the fresh, sharp-edged flows that would suggest anything erupting there recently. Without ongoing eruptions bringing fresh gas up from below, there is little left today to replace whatever the solar wind and the planet's own heat continue to strip away. A supply line that shut down long ago cannot refill anything happening now. Some smaller, more recent-looking vents have been proposed in isolated spots, though none confirm anything close to ongoing large-scale activity. The comparison with Venus could hardly be sharper. One world keeps topping up its atmosphere even now, and the other stopped doing so ages before anything alive existed to notice. Mercury does carry a magnetic field of its own, discovered when the Mariner 10 spacecraft flew past in 1974 and detected it directly. That same spacecraft carried instruments sensitive enough to catch even a weak signal, sensitive enough that a strong field would have been impossible to miss entirely. That field is real, generated deep inside the planet, though it reaches only about 1% of Earth's own strength. Its existence complicates any simple story about magnetic fields protecting atmospheres. Here is a small, rocky world that clearly can generate a field of its own, and it still cannot hold on to anything close to a proper atmosphere. Confirming the discovery required more than one pass, since a single brief reading could always have been dismissed as instrument noise rather than a genuine planetary field. Having a field is not the same as having one strong enough to matter against Mercury's heat and its weak grip on gas. This detail matters for the bigger picture. A magnetic field by itself does not decide whether a planet keeps its air. Mass matters more than any magnetic field does, and the heat a world sits in matters more still, with distance from the sun feeding that heat, without settling the outcome on its own. Earth itself makes the point from the other direction, holding both a strong internal field and a thick atmosphere at once, without either one fully explaining or requiring the other. Whether or not a planet happens to generate any field at all sits well down the list of things deciding its fate. Useful for deflecting particles, but never the deciding factor on its own. Mars offers a further comparison still, having lost most of its own field long ago, yet still retaining a modest, thin atmosphere, held mainly by other factors. Venus proves the opposite side of the same point. No internal field whatsoever, and yet it kept its air anyway. Push the comparison further, and the pattern looks less like coincidence and more like something dependable. A world with more mass and less heat tends to hold on to its air. A world with less mass and more heat tends to lose it. Run the same rough comparison against Earth and Mars, and the same general rule holds up reasonably well there too, even though neither of those two worlds sits nearly as close to the Sun as Venus or Mercury do. Gravity, temperature, solar wind exposure, and volcanic resupply all point the same direction for both Venus and Mercury, with no factor pulling against the others in some messy tangle. When several separate forces all lean the same way at once, the outcome stops looking like luck. Scientists building models of planets around other stars now apply this same rough rule as a starting point before adding in more detailed local conditions. One pattern playing out in opposite directions from a single set of rules. Picture the two worlds swapping addresses for a moment, purely as a thought experiment. A body with Mercury's weak gravity dropped into Venus's spot near the Sun would likely struggle just as hard to hold on to a thick atmosphere, no matter how close or far it happened to sit from any star. Its atmosphere, if it ever built one worth the name at all, would likely stay thin and be lost again within a comparatively short stretch of time. Low gravity is low gravity wherever it ends up parked. Distance changes the temperature and the strength of the solar wind hitting a world, but it does very little to change how tightly that world's own gravity grips the gas sitting above it. Engineers who study planetary habitability sometimes run exactly this kind of swapped scenario through computer models, just to see how sensitive the outcome really is. Move the address, and the outcome barely shifts. Now flip the thought experiment around. A body carrying Venus's mass moved into Mercury's tight orbit close to the Sun would likely fare better at holding on to some kind of atmosphere, even if that atmosphere ended up thoroughly cooked by the extra heat. Some of the lighter gases inside it would still likely boil away rapidly under that much extra heat, even if the heavier ones lingered close to the surface. Gravity does not care about the local weather. Strong gravity keeps doing its job regardless of how hot the neighborhood gets, even though the composition and thickness of whatever survives would look nothing like Venus's current blanket. The exact recipe would surely change under that much added heat. What would very likely survive is having an atmosphere at all, in some form. Mass, more than location, decides whether a planet gets to keep one in the first place, regardless of exactly how close to a star that planet ends up settling. 3 separate levers decide how this plays out for any rocky world sitting near a star. Distance decides how much heat and solar wind a planet receives in the first place. Mass decides how firmly that planet can hold gas against all that heat. Ongoing volcanic activity decides whether losses ever get replaced or simply pile up unanswered over billions of years. None of the 3 levers acts as a tiebreaker entirely on its own. A planet's fate only becomes clear once every one of them gets weighed together at the same time. Venus and Mercury landed on opposite ends of all 3 levers, and that is exactly why their skies ended up looking nothing alike. Mercury's own surface sits underneath almost none of that protection, bare rock waiting just beneath a sky with almost nothing left in it. What passes for an atmosphere on Mercury is not really a connected layer of gas at all. Scientists call it an exosphere instead, a name for something so thin and scattered that individual atoms drifting above the surface almost never collide with one another. Each atom follows its own separate arc, rising from the surface, curving upward under gravity, and falling back down again, largely on its own path rather than bumping into neighbors along the way. Individual atoms sometimes travel for hours before finally settling back down onto the surface again, somewhere else entirely. There is no wind in the ordinary sense, because wind requires enough molecules pushing against each other to move as a group. A handful of atoms scattered across a whole planet does not behave like the thick, churning gas found lower in Venus's own clouds. Describing it with the word atmosphere at all, some researchers argue, risks giving newcomers the wrong impression of what actually surrounds the planet. Mercury's sky, if it can even be called that, is closer to a slow scatter of individual particles than to any kind of connected weather. The atoms making up this exosphere come from a short list of sources, rather than any single origin. Oxygen, sodium, hydrogen, helium, and potassium each drift above the surface in trace amounts, arriving there by different routes. Concentrations of each ingredient shift noticeably, depending on the time of day and the current strength of the solar wind sweeping past the planet at that moment. Some get delivered directly by the solar wind itself, embedded in the stream of particles constantly striking the planet. Others get knocked loose from the ground whenever a tiny meteoroid strikes the surface, vaporizing a speck of rock into a puff of gas that briefly joins the exosphere above it. Sunlight itself can also knock atoms free directly, a slow process called photon-stimulated desorption that nudges particles off the surface one at a time. Mariner 10 detected the lightest of these gases. Telescopes on the ground later picked out sodium and potassium, and MESSENGER measured the whole mix from orbit. This whisper of gas, thin as it is, still manages to gather itself from several different directions at once. Sodium makes up one of the more visible ingredients of that thin exosphere, and it behaves in a striking way once it drifts free of the surface. Radiation pressure from sunlight and the ongoing push of the solar wind together sweep these sodium atoms into a long, faint tail streaming away from the planet, not unlike the tail trailing behind a comet. The tail brightens noticeably whenever Mercury passes closest to the Sun, since both radiation pressure and the solar wind grow stronger the nearer the small planet swings inward. Ground-based telescopes have followed Mercury's sodium since the middle of the 1980s and have watched the tail itself stretch, brighten, and fade since the early 2000s. The tail never grows bright enough to see with the naked eye from Earth. It shows up clearly enough in specialized instruments tuned to the exact wavelength sodium gives off. Similar sodium tails have since been searched for around other small airless bodies close to the Sun, using Mercury's own tail as the guiding example. This nearly airless planet still manages to leave a faint trail behind it as it moves. Surface pressure on Mercury runs at less than 1/1,000,000th of the pressure sitting at Earth's own surface, a number so small it barely registers as anything beyond the vacuum of open space. Instruments built to measure it strain to detect a meaningful difference between conditions right at the ground and conditions found many kilometers above any planet's surface. Even a sensitive barometer carried down to Mercury's surface would struggle to register a meaningful reading against that near-total vacuum surrounding it. For comparison, Venus presses down with roughly 90 times Earth's own pressure, a gap so wide between the two neighbors that they might as well belong to different categories of world altogether. One measures its air in tons, pressing on every square meter. Mars, sitting much farther from the Sun, still manages a surface pressure many times greater than anything measured on Mercury, despite its own thin atmosphere. The other barely measures anything at all. Without any real blanket of air to hold or spread its heat, Mercury's equator swings to some of the most extreme temperatures found on any planet's surface. During the day, sunlight strikes the ground directly and heats it, with nothing overhead to soften or redistribute that energy. Surface temperatures near the equator climb to roughly 430 degrees Celsius under the full glare of noon. Instruments carried by orbiting spacecraft have mapped this daytime heating in careful detail, tracking how temperature climbs steadily as the Sun rises higher above any given patch of ground. Nothing rises to meet that heat and carry it elsewhere the way even a thin atmosphere might. The rock simply absorbs what lands on it and holds that heat right where it fell. Even brief stretches of local afternoon on Mercury can register some of the highest ground temperatures ever measured among the rocky planets. Bare ground, hit directly by a nearby star, has nowhere to pass its heat along to. Turn to the night side of that same equator, and the picture flips completely once the Sun goes down. With no atmosphere present to trap even a trace of the day's heat, that same patch of ground radiates its warmth away into space rather quickly once sunlight stops striking it. By the time night settles in fully, surface temperatures can fall to roughly -180 degrees Celsius. Spacecraft measuring this nighttime cooling directly have confirmed just how quickly bare rock can shed its stored heat once nothing overhead holds any of it back. Nothing overhead holds any of that daytime heat back for later. The ground simply lets it go, all of it, into the dark. Engineers designing any future lander built to survive Mercury's night have had to plan around this rapid, extreme cooling as a central design constraint. This planet, with almost no air, keeps none of the day's warmth once the Sun moves on. Put the daytime high and the nighttime low from that same patch of ground side by side, and the gap comes out to roughly 600 degrees Celsius. That swing between noon and midnight is the widest recorded on any planet we know of. Venus, by comparison, barely notices the difference between day and night at all, its own blanket spreading heat so evenly that the two sides sit within a few degrees of one another. Mercury's ground has no such comfort. Engineers planning future missions to Mercury have to design for both extremes at once, building equipment able to survive baking heat and bitter cold within the very same stretch of ground. Each patch of its surface bakes under direct sunlight and then plunges into cold within the very same day. Few environments studied anywhere in the solar system demand quite this much resilience from a single set of instruments within one continuous stretch of ground. Extremes like these are what happens when a world is left with almost nothing standing between its rock and the raw temperature of open space. 600 degrees between noon and midnight does more than test a thermometer. It works on the rock itself. Every day-night cycle expands a boulder's outer skin more than its cooler core, then lets it contract again as the temperature falls. And that mismatch drives tiny cracks a little further with each cycle. Multiply that by billions of Mercury days, and boulders slowly split into gravel, gravel into finer dust, without a single drop of rain or gust of wind touching any of it. Dig down a short way, though, and the picture changes. A few tens of centimeters beneath the loose surface, the daily swing has already faded to almost nothing, and the ground settles into a temperature that barely shifts from one Mercury day to the next. Heat crawls through loose rock and dust far more slowly than it moves through solid metal, and it fades away with every centimeter it manages to travel. Even a day as long as Mercury's gives that warmth time to reach only a short way below the ground. Venus never needs that kind of underground refuge, since its day and night hardly differ to begin with. On Mercury, only depth offers real shelter from that swing, and that shelter starts only a short way underground. Mercury experiences nothing that could honestly be called weather. There is no wind moving dust or sand across the ground, because moving dust that way requires enough gas pushing against it to matter. There are no clouds forming anywhere overhead, because clouds need moisture and a churning atmosphere to gather and organize around. There is no rain, no fog, no storm of any kind ever recorded there. Even the thin layer of dust already sitting on Mercury's surface stays largely undisturbed for this same reason, with nothing around to stir it into anything resembling a storm. Every surface feature that exists on Mercury got shaped by something other than weather: impacts, ancient volcanism, or the planet's own slow cooling. Photographs and video gathered by cameras in orbit above Mercury show a stillness that never changes from one image to the next, frame after frame. Without any real atmosphere, a world simply has nothing left to make its own climate happen. Stand on Mercury's surface at the height of local noon, and the sky overhead would not glow blue or white the way it does on Earth. Without any real gas present to scatter sunlight in every direction, there is nothing to spread that light across the sky the way Earth's own atmosphere manages to do so effectively. The sky would instead appear black, the same black seen from orbit, even with the sun blazing directly overhead. Photographs taken by orbiting spacecraft confirm exactly this effect, showing a stark black background surrounding the blazing disk of the sun, even at local midday. The stars would still be up there, though an eye adjusted to that blazing ground would never pick them out. Earth's blue sky and Mercury's black one trace back to the same physics, applied to two very different amounts of air. Astronauts who have observed similarly airless conditions from the Moon describe much the same kind of stark black sky, even under full sunlight. One planet scatters its daylight into a soft glow. The other keeps it as one blinding point surrounded by darkness. Sound needs something to travel through, some medium of molecules bumping into their neighbors one after another to carry a vibration along. Mercury's exosphere is far too thin and far too sparse to do that job in any meaningful way. Drop something onto the ground there, and whatever vibration that impact produced would have essentially nowhere to go beyond the immediate point of contact. Engineers sketching out future landers for Mercury plan around radio signals instead of sound for any kind of remote diagnostics, since nothing there could ever carry an audible warning. No footstep could be heard by anyone standing nearby. No wind could ever howl. No voice could ever carry across open ground. Mercury's surface sits in a silence that has nothing to do with peace or emptiness of feeling. Recordings gathered on missions to genuinely airless worlds have to rely entirely on vibrations picked up directly through solid contact with the ground. That silence is simply what a world with almost no air sounds like, structurally from the ground up. Every atom that leaves Mercury's rock does not automatically leave the planet for good. Sunlight and impacts from tiny meteoroids knock particles free from the surface, and most of those particles never escape at all. They arc up briefly under gravity and fall back down somewhere else on the ground, only to be knocked loose again later. A smaller share gets caught by sunlight and turned into charged particles. And once that happens, the solar wind can sweep them into space for good. Only that charged portion truly leaves Mercury behind. Everything else simply migrates from one patch of ground to another, because so much of what gets knocked loose eventually lands again. The planet's overall stock of atoms barely changes, even after billions of years of this constant churn. Adding up every atom lost this way since Mercury formed still comes out to a vanishingly small sliver of its total mass, far too little to have shaved any meaningful weight off the planet itself. Constant motion then, without much constant loss. Erosion on most worlds relies heavily on moving air or water to wear down sharp edges over time, smoothing crater rims and rounding off jagged terrain bit by bit across millions of years. Mercury has neither of those forces available to it in any meaningful amount. Craters blasted into its surface billions of years ago remain remarkably sharp-edged today, their rims still standing crisp rather than worn soft, the way similar features would look on a world with real weather. Some of the very oldest, most heavily cratered terrain on Mercury has likely stayed essentially unchanged in its broad outline for more than 4 billion years running. Dust does shift slightly under the constant bombardment of micrometeorites, but nothing sweeps across the surface the way wind or rain would elsewhere. A landscape carved almost completely by impact keeps that record intact for billions of years rather than losing it gradually. Comparing crater counts across different regions of Mercury has become one of the main tools researchers use to estimate the relative age of each patch of ground. Mercury's face today looks astonishingly close to how it looked not long after it finished forming. Being close to the Sun does not automatically mean a planet gets wrapped in comfortable warmth the way that phrase might suggest. On a world with a real atmosphere, that closeness could translate into heat spread gently and evenly across a whole globe. On Mercury, with almost nothing standing in the way, that same closeness simply means more raw energy delivered directly onto bare rock, with nothing available to soften, spread, or hold on to any of it. A lander set down hypothetically on that bare rock would record heat arriving directly and immediately, with none of the gradual build-up a real atmosphere would otherwise provide. Proximity, without an atmosphere to manage it, is not comfort so much as exposure. Engineers have used exactly this reasoning when designing heat shields for any spacecraft planning to operate this close to the Sun for any length of time. What that exposure has done to the ground itself over billions of years is written directly into Mercury's own surface. At first glance, Mercury's grey, crater-covered surface looks less like a planet and more like a second moon wandering loose through the inner solar system. Its ground carries the same kind of dense, overlapping scarring found across much of Earth's own moon, the record of billions of years spent absorbing impacts with almost nothing to erase them afterward. Color photographs reveal it as a fairly uniform grey-brown, broken only by the brighter rays of debris thrown out from its more recent craters. The resemblance is only skin deep. Even experienced planetary scientists sometimes rely on subtle differences in crater density and color to tell the two worlds apart in an unlabeled photograph. To an untrained eye, scanning a photograph quickly, telling Mercury apart from the Moon, takes a careful look. Early telescope observers, working with far less detail than modern spacecraft provide, sometimes described Mercury using language borrowed directly from lunar observation. Underneath that resemblance, though, sits a very different planet with a very different history and a core unlike anything found inside its rocky look-alike. Mercury's largest scar, the Caloris Basin, stretches across roughly 1,550 kilometers of the planet's surface. That makes it one of the largest impact basins found anywhere in the solar system, rivaling similar giant basins recorded on the Moon and on Mars. Researchers first mapped its full extent using data gathered during the original Mariner 10 flybys, later confirmed and refined using far more complete imagery gathered decades afterward. Its floor is fractured into a maze of ridges and cracks, evidence of the ground settling and buckling long after the impact that carved it out. Mountains ring its outer edge, marking where material was thrown upward and outward during the original collision. Standing high on its mountainous outer rim, an observer would see the ground fall away further than from almost anywhere else on the planet. One strike, deep in Mercury's early history, left a mark large enough to be picked out clearly from spacecraft photographs taken from far above. That giant basin was gouged out roughly 3.8 to 3.9 billion years ago, during a period when large impacts were still common across the young inner solar system. Its rim still stands today as a ring of mountains rising close to 2 kilometers above the surrounding plains. Later, smaller impacts have pockmarked that same rim further, without ever managing to erase its original dramatic shape. Almost 4 billion years of subsequent history, including smaller impacts, quakes and slow cooling, have not been enough to wear that rim down to nothing. Mountains built by one violent event have simply outlasted nearly everything that came after them. Dating a feature this old relies on counting smaller, later craters scattered across its floor, and comparing that count against similar surfaces elsewhere. Time has barely touched what one ancient collision put in place. On the exact opposite side of the planet from Caloris lies a strange tangle of jumbled hills and grooves that researchers simply call weird terrain, for lack of a tidier name. The leading explanation holds that shock waves from the original impact traveled through Mercury's whole body and converged precisely on that far side, focusing enough energy there to fracture and scramble the surface into this unusual jumble. It remains a model built from geometry and physics rather than something anyone watched happen directly. Similar antipodal terrain has since been proposed at other large impact basins found elsewhere in the solar system, lending the idea broader support beyond Mercury alone. Still, the coincidence of location, sitting almost exactly opposite the impact that formed Caloris, makes the seismic explanation difficult to dismiss. Researchers studying the region continue refining exactly how the seismic waves would have needed to travel and converge to produce the jumbled terrain observed there today. One ancient collision appears to have reshaped two very different patches of the same small world at once, one directly and one from clear across the globe. Long cliffs called scarps cut across wide stretches of Mercury's surface, some of them running for hundreds of kilometers and rising several kilometers above the terrain on either side. They cut straight through craters, mountains and plains alike, without regard for whatever feature happened to be sitting in their path beforehand. Their presence tells a story less about impacts and more about the planet's own interior slowly changing shape over time. Some scarps rise abruptly enough to have posed a genuine challenge for engineers planning where a future lander might safely set down nearby. Unlike jagged crater rims, scarps have a smoother, more continuous look, curving gently across the landscape rather than breaking sharply at any one point. Mapping the full extent of these scarps required combining imagery gathered across both the Mariner 10 and Messenger missions, decades apart from one another. Mercury's surface carries the marks of two very different kinds of violence, one arriving suddenly from outside and one unfolding slowly from within. These scarps formed as Mercury's interior slowly cooled and contracted across billions of years. The planet's own volume shrinking bit by bit as heat leaked away into space. As the inside shrank, the outer crust had nowhere to go but to crumple and buckle to keep pace with the smaller sphere sitting underneath it. Think of the wrinkled skin of a piece of fruit left out to dry, its surface folding inward as the moisture underneath slowly disappears. Estimates suggest Mercury's overall diameter may have shrunk by several kilometers across its history, a modest number that still had to be absorbed somewhere across the crust. That comparison is rough, but it captures the basic idea well enough for anyone picturing it for the first time. Similar, though generally smaller, wrinkle features have also been identified on the Moon, suggesting this particular kind of shrinkage is not unique to Mercury alone. In effect, a whole planet has been quietly shrinking and wrinkling for billions of years, and its cliffs are the visible proof. Beneath that wrinkled crust sits an unusually large iron core, estimated to take up roughly 85% of the planet's own radius. Proportionally, that makes Mercury's core larger relative to its own size than the core of any other planet in the solar system. That much metal, concentrated so close to the center, also shapes how strongly the planet's own gravity pulls compared with its modest overall size. Earth's core, by comparison, occupies a noticeably smaller share of the planet surrounding it, leaving far more room for mantle and crust layered above. Mercury, by contrast, is mostly metal core, wrapped in only a thin shell of rock. Determining the core's exact size required combining gravity measurements gathered by orbiting spacecraft with careful modeling of the planet's overall structure. Weigh the two worlds side by side, and Mercury carries most of its mass in a place most planets keep comparatively modest. Why Mercury ended up with a core this disproportionately large remains genuinely unsettled among researchers studying the planet. One leading idea proposes an enormous early collision, a strike violent enough to blast away much of the planet's original rocky outer layer and leave the dense core behind relatively intact. A second idea points instead to intense heat very early in the solar system's history, hot enough to vaporize and drive off much of the lighter rocky material before it ever had the chance to settle into a proper crust. A later mission with sharper instruments may finally settle the question, measuring the core's structure in far greater detail than anything gathered so far. Both explanations remain active candidates, and neither has been confirmed decisively over the other using evidence gathered so far. Samples returned directly from Mercury's surface, something no mission has yet attempted, would likely settle the debate far more quickly than remote measurements alone. Whichever story is eventually confirmed, the result sitting at the center of Mercury today stays the same. A small, rocky shell wrapped tightly around an oversized metal heart. That oversized metal core also makes Mercury one of the densest planets in the solar system, packing a remarkable amount of mass into a comparatively small sphere. Only Earth comes close to matching it, once the extra compression from Earth's much larger size and gravity gets properly accounted for. By raw, uncompressed density alone, some calculations even place Mercury ahead of every other planet in the solar system, Earth included. Most of that density traces directly back to the sheer proportion of iron sitting at Mercury's center, rather than to anything unusual about its outer rocky shell. A small planet, the smallest of them all, manages to punch well above its size when it comes to raw density. Comparing Mercury against Earth this closely on this particular measurement is unusual, since the two planets differ enormously in almost every other respect. a core too big for the planet around it, and a planet too small for the core inside it. That is Mercury in a single line. Mercury's magnetic field is generated by motion deep within that same oversized core just described, not by anything happening in the rocky shell around it. For a small, slowly cooling planet to keep producing a field at all, some portion of its core needs to remain liquid and moving rather than solid and still. Current evidence points toward exactly that, a core still partly molten today, with metals circulating slowly enough deep inside to sustain the dynamo process responsible for any planetary magnetic field. Measuring the exact size of that liquid layer from orbit remains an ongoing challenge, pieced together indirectly from subtle wobbles in the planet's own motion. Researchers did not expect a world this small to still be running that kind of internal engine after billions of years of cooling. Understanding exactly how a core this small can sustain a working dynamo at all continues to challenge existing models of how planetary magnetic fields form. Mercury's core has not finished cooling and settling yet, and its magnetic field is the outward sign of that unfinished business. At Mercury's poles, the floors of certain craters never receive any sunlight at all, and instruments studying those permanently shadowed floors have confirmed the presence of water ice sitting there. Neutron measurements taken from orbit detected the telltale signature of hydrogen concentrated right where those shadowed floors sit, a strong indirect sign of buried ice. Radar observations, gathered separately using large dishes on Earth, produced bright reflective signals from those same crater floors, consistent with ice rather than bare rock. Researchers estimate the total amount of buried ice at these poles could measure in the billions of tons, though the exact figure remains an active area of study. Together, these two independent lines of evidence point toward the same conclusion using completely different methods. Later missions have continued refining these early measurements, narrowing down more precisely where the thickest deposits of buried ice are likely to sit. Finding frozen water tucked into the coldest corners of the planet closest to the Sun still counts as one of the more surprising results to come out of Mercury exploration. What keeps that ice from ever melting away comes down to simple geometry, rather than anything unusual about the ice itself. At Mercury's poles, the Sun never climbs high enough above the horizon for its light to reach directly down into the deepest parts of certain craters there. The tall walls surrounding those crater floors block every possible angle the sunlight could otherwise take to reach the bottom. Similar permanently shadowed regions exist near both poles, not just one, doubling the total stretch of hidden ground tucked away in permanent darkness across the planet. Shadow that never breaks day after day, for as long as the crater has existed, keeps whatever sits at the bottom locked at a permanently cold temperature. Nothing about the ice or the rock underneath it is special in any other way. Engineers studying these permanently shadowed regions have proposed them as possible resource sites for any future crewed mission venturing this deep into the inner solar system. Geometry alone, the simple angle at which light can and cannot fall, is doing all of the work in these particular, permanently dark corners. The Venera program's later landers carried more than cameras. Some carried a mechanical arm built to drill into the ground and pull a sample back inside for study. That arm bit into the rock outside and ground loose a small core. It drew the core back through an airlock into a sealed chamber built to hold a gentler climate than the world outside, cooled and kept at a fraction of the pressure crushing the hull. Inside that chamber, an onboard X-ray instrument bathed the sample in radiation and read off which elements answered back, working out the rock's chemistry without any of it ever leaving the protected shell. That whole sequence had to fit inside the same brief working life every Venus lander faced. What came back settled a real question. The ground at two different sites turned out to be basalt of two different kinds, one richer in alkalis than most volcanic rock, the other close to the ordinary basalt that floors the oceans of Earth. That fingerprint came from beneath Venus's own clouds, read out in the last minutes before the heat silenced the instrument for good. Mariner 10 became the first spacecraft to ever visit Mercury, flying past the planet 3 separate times between 1974 and 1975 using a single, carefully engineered trajectory. Engineers had to plan each flyby's path with extreme precision, since a small error early on could have sent the spacecraft missing the planet completely on a later pass. Each flyby captured images of a different portion of the surface, and together these passes mapped somewhere close to half of the whole planet for the first time in human history. The same mission also returned the first direct evidence of Mercury's magnetic field. Fuel limits and orbital mechanics meant the spacecraft could only fly past rather than settle into orbit around the planet it was studying. Data from those 3 flybys kept scientists busy analyzing images and measurements for years afterward, long after the spacecraft itself had gone silent. Just a handful of brief passes was enough to transform Mercury from a blurry telescope smudge into a real mapped world, one with a magnetic field and a battered face of its own. Messenger became the first spacecraft to actually settle into orbit around Mercury, arriving in 2011 after a long, looping journey and remaining there until 2015. Over those years in orbit, it mapped the planet's whole surface in detail for the first time, filling in the roughly half that Mariner 10 had never been able to photograph decades earlier. Its long stay in orbit also allowed researchers to track subtle seasonal changes in the exosphere, something no earlier flyby mission had ever had the time to observe properly. When its fuel finally ran out, mission controllers let the spacecraft's orbit decay on purpose, sending it down for a planned impact onto the very surface it had spent 4 years studying so closely. Its detailed gravity measurements also helped refine estimates of the size and likely composition of the core sitting beneath Mercury's cratered surface. What Mariner 10 had only sketched in outline, Messenger filled in almost completely, crater by crater, mineral by mineral. Bepi Colombo, a joint mission between the European Space Agency and Japan's JAXA, launched in 2018 on a journey far longer and stranger than a straight line toward Mercury might suggest. Rather than heading directly for the planet, the spacecraft spends years looping past Earth, Venus, and Mercury itself repeatedly, using each flyby's gravity to shave away speed a little at a time. Along the way, the mission also carries instruments built to study Venus's own atmosphere briefly during its passing flybys there, gathering bonus data on a world it only ever visits in passing. Mercury sits so deep inside the Sun's own gravitational pull that arriving too quickly would send any spacecraft racing straight past it or crashing in far too fast to settle into a stable orbit. Slow, patient braking through repeated gravity assists is for now the only practical way to arrive gently enough to stay. 2 separate orbiters, one built by each partner agency, will eventually separate from each other once the spacecraft finally settles into place around Mercury. Getting to the innermost planet takes far longer than getting to worlds sitting much farther away. The 2 worlds attracted very different levels of attention across the history of planetary exploration, driven by very different motives. Venus drew intense early interest, partly because, for a while, some scientists hoped it might hide conditions closer to Earth's own beneath those thick clouds, a hope that early landers eventually dismantled altogether. That early hope surrounding Venus faded quickly once landers reported back scorching heat and crushing pressure rather than anything remotely welcoming. Mercury, by contrast, spent decades being passed over, partly because reaching it safely takes so much more fuel and planning than reaching almost anywhere else, and partly because its harsh, airless, cratered face never held out much promise of anything resembling home. One world got explored first out of hope. The other got explored later out of sheer engineering stubbornness, once curiosity about it finally won out. Public fascination followed a similar pattern, with Venus capturing imaginations first and Mercury only slowly attracting comparable attention decades later. Different reasons sent spacecraft toward each of these two neighbors, and both sets of reasons proved well worth following. Today, both worlds do double duty as natural laboratories for a completely different branch of astronomy: the study of planets orbiting other distant stars. Venus's runaway greenhouse effect offers researchers a real, physical example of what can happen when a rocky planet traps too much of its own heat. A warning sign astronomers now watch for when studying atmospheres detected around planets light years away. Mercury's stripped, almost airless surface offers the opposite kind of example, showing what a rocky world close to its own star can look like once nearly everything volatile has been lost to space. Comparing both planets side by side gives researchers a rare, close-up pair of worked examples, tested cases sitting right next door rather than scattered light years away. Together, these two nearby, thoroughly studied planets give astronomers a working range of outcomes to compare against far more distant, far less understood worlds. Astronomers searching for potentially habitable worlds around distant stars now routinely check new candidates against the extremes both Venus and Mercury represent. Two planets close enough to visit directly are quietly teaching scientists what to expect from planets that may never be visited at all. Step back now from every detail already covered, and both worlds trace back to one shared starting point. Two rocky, moonless planets, born close together near a young sun, closer to it than Earth ever sits. Nothing about that early resemblance hinted at just how differently the two would end up looking billions of years later. From there, their paths diverged sharply. One world ended up under an air blanket so thick the ground beneath it never stops being squeezed, trapping heat so completely that its surface stays hot enough to melt metal day and night alike. The other lost nearly everything it might once have held on to, left with bare grey rock, a battered face full of ancient scars, and barely a whisper of gas drifting above it. At that very early stage, an outside observer might have guessed their sizes were more similar than their radically different fates would ever suggest. Same origin, same rough starting materials. Two very different outcomes written by gravity, heat, and time. The difference between these two worlds was never really about size alone, and never only about distance either. It comes down to how firmly a planet's gravity can hold on to gas against the heat pressing in from its star. How much that heat gets amplified by proximity to the sun in the first place, and whether volcanic activity keeps replacing whatever slips away into space over time. Balance those three factors one way, and a world ends up wrapped in cloud thick enough to crush and cook almost anything sent to study it. Balance them the other way, and a world ends up bare, cratered, and swinging between blazing heat and bitter cold as each day gives way to night. Venus and Mercury are not opposites by accident. They are what happens when the very same short list of rules gets applied to two different rocky worlds sitting at two very different distances from the same star. We began this journey with two rocky neighbours starting from the very same point. No moons, nothing between them at the start but size and distance, born from the same hot inner swirl of dust around a young sun. From there, we sank deep into Venus, into clouds of sulphuric acid that never part, air 90 times heavier than our own, heat enough to melt lead, and a slow greenhouse effect that turned a possible ocean into a scorched, waterless world. We rode the fierce winds circling high above those clouds, traced volcanic plains mapped only by radar, and lingered over hints that some of those volcanoes may still be quietly active today. Then the road turned, and the question changed from what keeps a world wrapped in air to what strips it away. We measured escape velocity, weighed gravity against heat, and watched Mercury lose almost everything Venus managed to keep. We drifted through Mercury's paper-thin exosphere, felt the 600-degree swing between its blazing noon and its frozen midnight, and stood in a silence with nowhere for sound to travel. We walked its battered, ancient face, from the vast colorous basin to the long cliffs left behind as its core slowly cooled and shrank, and found water ice hiding untouched in craters sunlight has never once reached. We followed the spacecraft that made all of this possible, from the patient, decades-long Soviet landers at Venus, to Mariner 10's brief glimpses of Mercury, to Messenger's careful years in orbit, to Bepi Colombo, still spiraling gently inward even now. Two worlds born side by side ended up further apart from each other than almost any two planets have any right to be. And the whole difference comes down to nothing grander than air. How much of it a world can hold, and how much of it slips quietly away. If drifting through a pair of small, strange worlds like this one is the kind of company that helps you unwind, a quiet subscribe costs nothing, and it helps this channel keep finding people who enjoy falling asleep to it. Let your eyes rest now. Let your breathing slow. And let the rest of this night be as quiet and unhurried as the dark side of a planet with almost no air left to disturb it. Sleep well.